Next speaker is Dominic from Cambridge. So everyone knows about monads and the nice glue notation for monads in Haskell. But Dominic's going to tell us about comonads and the nice notation for comonads. Right?
That's right.
Go ahead.
Hopefully. That's good. So, before I talk about comonads, I want to talk about context dependence in languages. So, while this is getting going, I'll just waffle for a bit. So, ever since Aristotle, people have thought about how language has weird properties of substitution and equality that are sort of pretty different to what goes on in mathematics. And Murphy's law continues.
Got 5 minutes left.
Don't get nervous. I don't know, my screen's just black.
I think this is
That's always the way,
Cambridge.
Hey! But I can't see. I think I must do to here.
Very tight.
Sorry. Anyone know any nice mat tricks?
Maybe you just give a blackboard over the
Yeah.
black panel.
Yeah. I tested it, it was all fine.
It is. I was here once.
Okay.
Do you have your keynote presentation open already?
Yeah.
And is it on full screen?
Yeah.
Don't kill the full screen.
How do I kill the screen?
Escape.
Escape. That does not work.
Has it got photos?
Well,
You need a Windows machine.
aha! Oh! Hey! Okay. I killed the, okay. Sorry about that.
It's all pretty easy with those Macs.
It always works.
They never crashed. Did you know that? Macs never crashed. They just
I
not
just did.
respond.
I have a counterexample.
And there are
Slightly better, is that?
and there are no problems. There are only situations.
Intended functionality. Just not what he intended. And this is such a
There's
situation.
instructions for the sales force.
Oh,
There are
right,
no
yeah.
problems. There are only situations.
Okay, okay.
You are a Mac person.
Oh, no,
Well, you have been in the past.
I have been in the public here. I'm slightly moving to the next again.
So shiny.
I have shiny apples.
Okay. Right. Okay, so I want to talk about context dependence. So here's two true statements. The number of planets is 8, and Kepler believed 8 is the third power of 2. Now, you're all smart people, so you might already be thinking, the number of planets is 8. That's an interesting statement. Until about 5 years ago, that was false. The number of planets was 9, and then Pluto got rejected, sadly. So, as lots of people know for thousands of years, when you try and substitute equal terms in natural language, things get a bit strange because of the wrong context. So, if I wanted to substitute 1 into 2, this would be a really stupid thing to do because it changes the truth of 2. So Kepler believed the number of planets is the third power of 2. And that's almost certainly false. In 1596, when Kepler wrote his famous work, he wrote about the 6 planets that they knew of. Here's another sentence. Kepler believed the number of planets is 6. Okay, that's true if we read his books. But again, if we substitute 1 into 3, that was a stupid thing to do because Kepler believed 86 is, I hope, false. Now, of course, the problem is that the number of planets changes. We change our definition, depends on your beliefs, maybe about Pluto things. It also depends on the time on which in which you have your scientific knowledge. So as people like Frege, Carnap, even Russell and Whitehead talked about, if you want to do substitution in context, it has to be within the right context. So we've got one, and we can substitute it into 3, but only for the definition of the number of planets in 1596 in Kepler's beliefs. And this preserves the truth of the statement. So the conclusion is that context dependence, whether it be depending on space and time, beliefs, this changes the rules of substitution. Here's one more sentence. It's a bit longer. And it's a bit random. Now, we can do this, we can substitute in the number of planets and the number of popes since Gregory XIII. If we do that both in the same context of 1596 and Kepler's beliefs, then yes, this preserves the truth of the statement. I looked this up. But if we substituted them at different contexts, maybe we looked ahead 9 years and substituted in the number of popes since Gregory XIII, which is now 7, then this was the wrong thing to do. So the conclusion is that if we want to substitute multiple context-dependent things, we need to do the substitution at the same context. Okay, this is all lots of things that lots of linguists know about, there's lots of books written about, but actually we have similar situations in programming. So let's get back to programming. So context dependence appears in programming in different ways. It appears in programming when we talk about having multi-threads or chunking up bits of data, but we can think about it even when we're just working on a single data type. So lots of programs we write have structured data, maybe lists, databases, trees, and we have lots of operations that manipulate these pieces of data. Many of these operations we can describe as a local transformation, as a local operation on a data type. So for example, with arrays, we might have some array B, and we have some index I, and we describe some transformation for the data based on current position I and maybe some neighborhood of elements. And then we have some boilerplate generic code that propagates this local, takes this local operation and propagates it to a global operation. So it extends it or promotes it. Now this is like a context-dependent operation. If we think of B as being the whole world, that gives us values for all the contexts. And these positions are context. So I is this current position in this local operation. And then our boilerplate applies the local operation at all contexts and collects together a new world for us. So another example is the live variable analysis. We have a control flow graph, and we want to, at a particular node in the graph, analyze what variables are live. So for a node S, we have some local operation, and then again we write some boilerplate in our program that exists in our compiler, which iterates over a control flow graph. And we might have lots of other operations which we can similarly plug into this global boilerplate code, which do some sort of some local operation on the graph. And here's one with lists. This computes pairs as it goes through a list, and it has some, again, some general iteration kind of code. So as programmers, when we're programming, we might see this pattern lots and think, okay, well, maybe we can abstract this as some higher order functions. Maybe we can come up with an algorithmic skeleton. So we've got some data type, let's call it C, which has this idea of positions, like a list. And maybe we have some notion of what is our current position in this data type. So our local operations have this kind of type. We take in this data type and we output a single value, which is the new value for the current position. We could think of something a bit more generic. There's a trivial local operation which just says project from the data type, give me the ith element in the array, for example. And we have this function which is this propagation, I want to take a local thing and make it global, the boilerplate iterative code. And it says this type. So I take one of the local operations, and I want to turn it into an operation that takes in the data type, gives me a data type back. So it goes from local to global. So we might come up with this as an algorithmic skeleton. And actually, this has the structure of a comonad. Comonads are dual to monads, so think about flipping the arrows round in the definition of a monad. And this is in what's called extension form, so it has this operator, which is a bit like a bind. And I'll call it extension for the rest of this talk. So if you compare this with functors, functors have the fmath operation. When we model them in, say, Haskell or ML or something, we have an operation like this, which tells us how to transform elements. And comonads are more general. Instead of getting just a single element, you get the whole data structure, which is sort of focused at a certain point, and we get to return new value from that data structure. So it's a generalization to functors. So I'll show you an example. So arrays with a cursor, which is a sort of pointer, a particular index into the array, is a comonad. So I'm going to use this little pictorial representation here. So this cursor gives us the current position. And a local operation is going to compute a new value at the cursor. So we're going to take in an array, and at the cursor position, this orange square, I might pull in some nearby values and produce a new value. So this operation here is the Gaussian filter on images that's quite common in image processing. So it does a blurring by taking a weighted average of a small neighborhood of pixels. And this is defined at some local position at ij within the array. So then we have this promotion operation that takes the local and turns it into a global. So that's the type. So say I start off with an array of a values. I have this f function. Then the extension of f gives me an array where I apply f to the array with the index moved along to every single position. So it's taking the local operation and applying it at every index. And then this reduces to an array of b's. So it's like a convolution operation in image processing. So for the Gaussian operator, here's an image of the Cambridge Computer Lab, and it blurs it. If I applied just the Gaussian operator to the image, that would just give me a single pixel. But it's this extension, the dagger operation, that applies it to the entire image. And so we have this current operation. This is the sort of unit operation of comonad, and this just projects out the current position. So if I apply that to the image, I get the same thing back. And so this is just the identity, and this is actually a law of a comonad. So what comonads provide is an operation to give you composition for these for functions with structured input. So if we have f and g, they take in arrays, they take in some data structure as input, but they don't naturally compose. But we can compose them by promoting the first one to a global and composing it with the second. So see that types show how they compose. And then the laws of a comonad ensure that this composition is associative and has units, which is the current. So if we think about these as context-dependent operations, say we've defined f as for all context I, and we have g defined as for all j, then the composition defines a local operation that's all defined at the same context. So defined at I, and so we replace the positions of j inside g with I. So they're composed together, and the f and g are going to be applied at the same position. So comonads are just like monads. They're a really nice design pattern for programming. We see them popping up in lots of places, and as you all know, monads are extremely popular in functional programming. So much so that Haskell has the nice do notation, which simplifies programming with them, abstracts all the operations. F# has the let bang syntax, which again abstracts the operations of a monad. But comonads haven't had a notation, so this is what we're proposing. A notation that's going to make it a bit easier for them to be used, so people can start using them in their programs, because the pattern does pop up a lot. So it's like a let binding style kind of block, like the do notation. Here's an example. I'm going to step through it line by line. It defines an operation that computes the contours for an image using our Gaussian filter and Laplace filter, which is similarly defined. So let's break it down. So a CODO block, differently to a do block, starts with a parameter, that's x here. So we've got a pattern which binds to a parameter. Because a CODO block defines one of these local operations, or co-quasi arrows as people call them. So x is bound as the incoming parameter, and it has one of these array types. So this is the typing rule. We see that x goes into the context with this type CT for some comonadic data type C, and then that's in context E for the rest of the block. So following this double right arrow, we have a block which comprises 0 or more of these binding statements that form pattern left arrow E. Now let's look at the types. The right-hand side of this binder is an expression, but it's treated as one of these local operations, and it's treated as a local operation whose parameters are all the preceding local variables in the block. So when we have this special left arrow, what it really means is extend this operation to a global operation. So this was the type of Gauss 2D, and X as this type. So the application just gives us back a float. But the type of Y is actually an array of floats. So what happens is the Gauss 2D operation with X is taken as a local operation from its inputs, X, and is extended using the operation of Comonad, the extension operation, to apply it to the whole image. So here's the typing rule. So E1 has type T prime, but after the binding happens, Y is a type CT prime in the scope of E2. And if we had sort of equals like a normal left binding here, then Y would be just a float. But then this would have the wrong type for the rest of the operation. So we have another binding, we do Gauss again, so we do 2 times Gauss filter, and we apply this to Y. So Y is the whole array of the Gaussian operator applied, and then we do it again, and we get Z as the whole array of 2 times Gaussian. Now this, we use current here just to project out of Y and Z. Now, yeah, Y and Z have those types as arrays, so when we do current, we project out the value under the index, and we subtract them. So importantly, each one of these local variables, x, y, z, w, they're all at the same cursor as x. So whatever the cursor or pointer is for the incoming x, all of these arrays have the same one. So this way, current y minus current z is the pointwise subtraction. And then our last thing, so the block is terminated by a final result expression, gives us this last float result, which does the inverts of the Laplace operator. Now, this defines the local operation, the contours operation, but again, if we apply this to an array, we just get 1 pixel, but we want to apply it to the whole array, so we do the extension of contours to apply it to an image. So the CODO notation is all about having a substitution, but that takes into account this context. So let binding corresponds to pure substitution, as we all know. It's sort of internalization of the substitution lemma. But CODO binding corresponds to substitution taking into account context. So going back to our Kepler example from earlier, we can write this in the CODO notation as we've taken our person Kepler, we maybe have some definition for the planets, some definition that's for popes, parameterized by the pope, and then we can say current planets equals current pope since, and give it Greg 13. Apologies to Gregory 13 for the abbreviation. So the Kepler parameter is some sort of comonadic data structure that contains all of this beliefs in the temporal context. And as we saw at the example, we needed to do this substitution in the same of planets and popes in the same context for the operation to make sense. So by the desugaring of this into the operations of the Comonad, planets and pope sims have the same context within the block, the same context as defined by the incoming parameter Kepler. So for our contours example, this meant that x, y, z, and w, as I said, are all at the same context, or they're sort of synchronized. Okay. So this really does simplify programming with Comonads. If I wanted to write contours by hand, I'd have to write something like this, which is a bit icky. The things get difficult when you have these sort of binary operations on comonadic functions. So just like the do notation just makes it nicer to work with monads, CODU notation makes it nicer to work with comonads. There's details of the desugaring in the paper. I'll show you just a little bit now. So I talked about how when we have the right-hand side of the binder, it's treated as a local operation from its preceding variables. So when we've got draws 2D applied to x, in the desugaring, this is turned into a function from x, and the extension operation is applied. And then this is composed with the rest of the block. Now, as you build up the context, things get a little more tricky, but if you want to look at that, have a look in the paper. So there's lots more examples of comonads. There's streams, graphs, trees, zippers. Any zipper is a comonad, because that gives you this notion of context when you have that sort of hole in the zipper. So the control flow graph example at the beginning, you can do live variable analysis like this using the CODU notation. You can build up other graph algorithms in your compiler just using one comonad for the control flow graph, and then using the notation to write down these operations. So to finish up, some people will be thinking about do and thinking like, well, shouldn't CODU be dual to do, and why does it look so different? So what monads provide is a way to compose functions which have structured output, essentially. We encode effects as an output, as a data type wrapping the output, so they have this type. Now comonads being the dual provide composition for functions with structured inputs, so they give you composition for functions of this type. So the do notation, when you write down do notation, it defines an expression of just type MA. But this is really equivalent to having sort of units MA. So there is some input, but because of the fact that all Haskell monads are strong, the desugaring is much more simple, and any of these inputs to the block are just the free variables, just the implicit free variables. So they don't need to be included as a parameter. So the type can just be units MA, and we just put that as equivalently as MA for simplicity. But CODU, the parameter, is really important because that gives us the input structure. That tells us what context we have, what's the whole universe that we're looking at. So we can't elide it, it has to be there. And usually, as I've shown with the images and things, we want a function that's CHCB, so we do the extension. The Comonadic axioms give us an equational theory for CODU, so just like do, there's some rules. Yeah. So try Comonads now. Edward Comet has the control Comonad package, which gives you the classes you need, and then you can pick up the CODU notation here, and there's some more examples. Thanks.
All right. Any questions for the speakers?
So how have you implemented the notations there? Pre-pass or?
Yeah, at the moment it's just a macro preprocessor. I mean, the desugaring is not too hard, so it doesn't have to pull apart expressions. It's just a simple sort of rewrite. So it's a macro, but maybe I'll get some enthusiastic undergrad to use or something.
Can you give some more examples where you could apply this?
Yeah.
So some sexy comonads, so to speak?
Yeah. So, as I'm sure you know, Ralph, one of my favourite languages in the world is the Lucid stream programming language, and you can embed that into Haskell using the CODU notation. Uslu and Vene had a nice paper where they gave a deep embedding of the Lucid language into Haskell. They gave an interpreter for Lucid. It's a sort of stream language. They gave it in Haskell, but using Kodu you can have it as a shallow embedded DSL with quite nice syntax. I quite like the arrays one because I have an array language which uses it. You can do the things with the graphs, trees as well, attribute grammars. You can write down with the Kodu notation as well. Jeremy.
So that suggests having a look at the Utrecht attribute grammar library and seeing whether you can tackle something like that with it.
Yeah, maybe.
Exercise.
Have a coffee.
Yeah. I'm sure it'll be quick.
Simple exercise left to the reader.
There might be some things which have a mix of comonadic and monadic things. So there is also a Baidu notation which for arrays where you take in a comonad and return a monad, but you need a distributive law between the two as well. And I don't think there's many examples of that.
Okay, and let's take the speaker again.
Thanks.